Hello students, welcome to Siri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 7 of our unit Magnetism and Matter. So let's begin with today's class. In today's session we are going to discuss about the hysteresis curve. So what hysteresis curve is and why it has been plotted. Let's have a look. We have plotted a graph for the H, which is a magnetizing force, for versus B, it's a flux density. Basically this has been defined for the ferromagnetic material. So initially the situation is that, let's suppose this is the a certain piece of a ferromagnetic material, and as you understand now that in ferromagnetic material it's a domain culture is there, that different domains are there and they have been aligned according to their own properties. Yes, so initially this was the domain culture, and all the domains have been arranged according to their own conveniency. Yes, now once this ferromagnetic sample is placed in the magnetic field and magnetizing force is being applied on it. So as you can see that as soon as this magnetizing force is keep on increasing, the flux density is keep on increasing. So now what suppose I'm going to do is I'm going to increasing the magnetizing force. So as magnetizing force is increasing, that it will increase the flux density, and we have reached to here. Now it is the situation when we say that all the domains or most of the domains have been aligned themselves in a single direction, something like this. I hope this is clear. So, but what I understand is that by increasing magnetic force, by increasing the magnetizing force, I can increase the flux density. So what I'm supposed to do is I'm still increasing magnetizing force, but after some time I realize that even though magnetizing force is in being increasing, flux density is not changing. So what I understand is that this is the saturation location where all the domains have arranged themselves in the direction of magnetic field, and now no more domains can be aligned. So this is the saturation beyond which no domains will align themselves in the direction of the magnetic field. So I understand, okay, this is the saturation location. Now what I understand is, what I want to look forward is that if I remove all the magnetizing force, or if I reverse the direction of magnetizing force, and if my magnetizing force is zero, what would be the situation? So I start decreasing the magnetizing force at a very surprise, that when my total magnetizing force is zero, still there is a certain flux density where there. So I wonder why it has been happen. Because what the situation is, even though you have removed all the forces and certain domains have de-aligned themselves, these are the cases of de-align themselves, but there are still certain domains, let's suppose, look at this, that they will keep themselves in the direction of the magnetic field. So this is what we call as a retentivity. Even though magnetizing force is zero, it will still behave as a magnet. This is the retentivity. I hope this is clear. So what I want is that, okay, this is clear that this at this point, or at this magnetizing force, it is h equals to 0. The still certain domains are there which are aligned in the direction of the magnetic field. So what I need to see is, what I want to observe is that if I'm still reducing, now it has been already 0, now if I'm applying a reverse force, yes, in the negative direction, what happens? So if I still decreasing the magnetizing force, and once a time has came where I got that all the magnets have de-aligned themselves, and that location of magnetizing force, when all the domains have de-aligned themselves, is called as the coercivity. So this is the situation where my flux density is 0. Yes, this is the value of that magnetizing force where all the flux density will be 0. Now if I still decreasing the magnetizing force, why I say magnetizing force, because I am applying decreasing, because why, because I am applying it in the opposite direction. So I'm applying the force in opposite direction, and even in the negative direction a location has arrived which is the saturation point, that beyond this point domains cannot de-align themselves. So I understood that okay, this is the maximum level, this is the maximum saturation level, beyond which you cannot de-align the domains of the ferromagnetic materials. Now what I do is I start increasing the magnetizing force in the positive direction, and I got this kind of curve. So this is the hysteresis curve. This is the hysteresis curve for the ferromagnetic material. I hope this is clear. This is clear. Yes? Great. Now, now this area, it's a B versus H graph, and area of this area will give me the, it's an energy loss per unit volume. It's an area of B versus H curve that will give me the energy loss per unit volume. It's a per cycle. So it will give me an energy loss per unit volume per cycle. Yes, even a same kind of graph, same hysteresis curve can be formed for the I versus H graph, and that graph also will give me the energy loss. It's, that means it's area of this I versus H graph give me the energy loss. When I say that B cross H graph is there, B cross H graph is there, its area will give me a joule per meter cube. While here unit, it's a unit of I versus H graph is ampere square divided by meter square. Please do remember these things. Yes, those are the very small things, but very important things. Yes, great. So please do remember this. This will also work for your school examinations, because this is one of the favorite topics of the school examiners. Now, now let's look at the analytical studies of the hysteresis curve of the soft iron and the steel. So we have drawn this two hysteresis curve, one for the steel, one for the soft iron. So you can observe that the retentivity of soft iron is greater than the retentivity of steel. One more thing, soft iron is more strongly magnetized than the steel. Yes, coercivity, look at this. Coercivity of soft iron is less than coercivity of the steel. So what we can conclude is soft iron loses its magnetization more rapidly than the steel does. Yes, even the retentivity of steel is, retentivity of soft iron is greater than retentivity of steel. So this is the graph for the hysteresis for the steel and the soft iron. So let's have a look at the question. It says the area enclosed by a hysteresis loop. What does it measure? It measures energy loss per cycle per unit volume. Great. Let's look at the next question. What does it say? It says property possessed by a ferromagnetic substance only is. Yes, this is the property possessed by the ferromagnetic only. It's a hysteresis. Yes, you are not going to plot hysteresis curve for any other material. Now let's look at the permanent magnets and electromagnets. So let's begin. We can say that this a soft iron does not have any magnetic field. But as you can see that now this soft iron is being connected with certain circuits. So when current flows in the wire, the soft iron becomes magnetized, and so a magnetic field is detected by plotting the compasses that we have. Compasses over here. Yes, so after plotting the compass I can understand that yes, magnetic field is there after current is being passed through that, and even direction of that magnetic field can be detected by the compasses. So we can say that substances which at room temperature retain their ferromagnetic property for a long period of time, are called as the permanent magnets. And this permanent magnets can be made in a variety of ways. One option is one can hold an iron rod in the north south direction, and we are going to hammer it repeatedly. So even this is the way how the permanent magnets can be formed. One more option is one can also hold a steel rod and struck it with the one end of a bar magnet a large number of times, which always in the same sense to make a permanent magnet. Even these are the cases through which we can make a permanent magnet. An efficient way to make a permanent magnet is to place a ferromagnetic rod, as you can see in the diagram, in a solenoid and pass a current. So the magnetic field of solenoid magnetizing the rod. That this is the situation when this solenoid is being connected with the circuit and a certain current is flowing. If current is flowing, we know that we studied this, that magnetic field inside the solenoid will be the mu naught into Ni. So if I insert a steel rod, or if I insert a rod into this solenoid, then this magnetic field mu naught Ni will magnetize the this this iron rod or steel rod, and it will make a permanent magnet. One more option, it's a material should have higher retentivity, so that the magnet is strong and higher coercivity. This magnetization is not going to be erased by the stray magnetic fields or temperature fluctuation or minor mechanical damages. Yes. Further, the material should have a high permeability. A steel is one favored choice. Yes, when we choose that which material is to be converted to permanent magnet, steel is always our choice. It has a slightly smaller retentivity than the soft iron, but this is outweighed by the much smaller coercivity of soft iron. Yes, so steel is favored choice. Steel is favored choice. Other suitable materials for permanent magnets are alnico, sorry, cobalt steel, and triconal. Core of the electromagnets are made up of ferromagnetic materials which have high permeability and low retentivity. Please do remember this. Soft iron is suitable material for electromagnets. So when I choose electromagnets, which I can say is the temporary magnets, soft iron is the suitable material. On placing a soft iron rod in a solenoid and passing a current, we increases the magnetism of the solenoid by a thousands of volt. So when we switch off the solenoid current, when we switch off it, the magnetism is effectively switched off, since the soft iron core has very low retentivity. So when I say low retentivity, once I switch off it, it will lose its magnetism because its retentivity is very low. I hope this is clear. So once you switch on it, it will behave as a magnet. Once you switch off it, it is not at all magnet. I hope this is clear. Great. So we can say electromagnets are used in the electric bills, loudspeakers, telephone diaphragms, at etc. Uh, the energy dissipated and the heating will consequently be small. So material must have a high resistivity to lower eddy current losses, and giant electromagnets are used in cranes to lift machinery and bulk quantities of iron and steel. So when we use a crane, we use the same principle, that very giant electromagnets have been employed to to lift machineries and bulk quantities of iron and steel. Yes, because once a current is being passed, it will behave as a magnet, and if I have kept the giant magnet, it can do a work for me. I hope this is clear. Is it clear? Is it? Yes, great. You can also see this that in certain applications the material goes through an AC cycle of magnetization for a long period. This is the same case. This is the same case in the transformer course and telephone diaphragms. So the hysteresis curve of such material must be narrow, as we have seen this. We have seen the hysteresis curve for the soft iron. Yes, it is the narrow one. I hope this is clear. Is it clear? Is it? Great. Let's look at certain MCQs. We can say that ferromagnetism is not found in, yes, it is there. It is going to found liquid and gases. It is not going to be there in the semiconductors. So this would be the correct answer because they have asked not found in. Second, a marine compass is used. Why marine compass is used? To compare magnetic moments? No. For determination of H? No. For determination of deep? No. It's a for determination of direction. Yes, this would be the correct answer. I hope this is clear. So let's just wind up this session over here. This is the theoretical session because this session is very important according to the certain questions have been asked in the previous years in mostly in the medical examinations. Yes, so but please go through this. You never know. NTA can ask anything. Thank you. Have a good day. Take care. Bye bye.